करो सभी, कैमरा ऑन। ये दिलगीर कौन है? कैमरा ऑन दिलगीर। सभी कैमरा ऑन करो ना, ये क्या हो रहा है? फास्ट हम शुरू करेंगे, कुछ आगे बढ़ेंगे। वैसे भी तुमने 2 दिन अच्छी खासी छुट्टी की। ओके, सो लेट्स स्टार्ट। तो मैं अपना ये स्क्रीन शेयर करता हूँ। सो लेट्स डू दिस वन। एक छोटा सा ही रिजल्ट है बेसिकली, द dual of bounded functions on some set. So it's okay. So let's see. हाँ, ये जो हम रिजल्ट्स कर रहे हैं, मोस्ट ऑफ देम या जो अभी करेंगे, दे आर ऑन रियल स्पेस। इसके बाद एक और रिजल्ट है मजूर-उलम थ्योरम, that would also be concerned with the real normal spaces, you know, where the field is real. So let me first define what do I mean by so L infinity, this set. Now given any subset, this subset क्यों मैं लिख रहा हूँ, any set D, define this small n infinity t, और जिसको हम कभी कभी BD भी लिखते हैं, bounded functions on D, which is actually all functions from D to the set of real numbers such that f is bounded. And you know that if I take D equal to set of natural numbers, it becomes L infinity, है ना, जो ना तुम जानते हो. So L infinity D है, L infinity D is a linear space under pointwise operations, obviously, कि अगर एक फंक्शन बाउंडेड है, दूसरी फंक्शन भी बाउंडेड है, उनका पॉइंट वाइज सम भी बाउंडेड होगा. सेम विद द स्केलर मल्टीप्लिकेशन. is a linear space under pointwise operations which is a Banach space. It's easy to show that it's a Banach space. It will work. जो हमने proof किया था for infinity, वही काम करेगा. I think Banach space, when equipped with the norm, why not you, तुम्हें शायद पुराना कुछ रिवाइज हो जाएगा इससे. Equipped with, अगर मैं इस पे norm ऐसे करूँ, subnorm with norm of f is equal to supremum x belongs to D, क्योंकि ये bounded है और this set, तो supremum exist करेगा. तो पहले तो ये दिखा दो, ये norm है, जो कि दो मतलब उसमें कुछ करना नहीं, सब कुछ फॉलो हो जाएगा. दूसरा, you show that it's complete, यानी it's a Banach space. So I leave it to you. मतलब ज्यादा कुछ करना नहीं, वो जो फंक्शन एनालिसिस फर्स्ट में L infinity पे किया होगा ना, इस वाले पे सिंपली थोड़ा सा लैंग्वेज को चेंज करना है. Okay. Now also for a set T, for a set D, we denote by P sub A on D to be a set of all finitely additive sign measures of bounded variation. Set of all finitely additive measures of bounded variation. इसको मैं थोड़ा सा explain करूँ, although it's not that complicated. On the, so you can write it. इसका मतलब ये है mu जो है, it's all types of functions from the power set of d to the set of real numbers, actually extended set of real numbers. लेकिन चूंकि हमने लिखा है finite, so it would be real numbers. Sign measure means it is क्या बोलते हैं, no, it takes real numbers as its range. इसकी range could be negative also, है ना? Measure cannot be negative, but sign measure, you know, is the extension of a measure, definition of a measure to the whole real line. And mu of phi is equal to 0, and it is finitely additive means mu of union I runs from 1 to n ei is equal to summation I runs from 1 to n mu of ei, where ei is a subset of t and ei intersection ej is equal to phi for all I not equal to j, I running from 1 to n. तो ये तो हो गया एक पार्ट इसका, एंड साथ में सुप्रीमम एक और प्रॉपर्टी, दिस सुप्रीमम ऑफ दिस सेट, ये सेट में सेट है, सुप्रीमम ओवर समेशन आई रन्स फ्रॉम 1 to n mu mod of mu ei is less than infinity where this t supremum runs over all these ei's, where d can be written as a union of measurable sets. यानी इसको कहते हैं हम a measure of bounded variation. यानी अगर तुम इसका कोई भी measurable partition लोगे तो फिर तुम उनमें से उनका measure देखोगे, so that would be always less than infinity. So we can also endow it with a normed space structure, you know, by you can define measure mu1 plus mu2 point wise, not point wise. Yes, you can talk about points, but if you treat sets as points, तो अगर तुम ऐसे लिखोगे, मतलब वही ना जो हम करते हैं वेक्टर स्पेस बनाने के लिए, so this is indeed a vector space, and इसका एक नॉर्म भी है, तो चलो मैं ऐसे लिखता हूँ alpha mu1 of e is equal to alpha mu1 of e for all mu1 mu2 belonging to BAT b sub ad, इसको क्या होगा b sub ad, मैं ऐसे लेता हूँ, मैं लिखता हूँ under the operations b sub ad is a vector space, and it's a normed space under the norm, वही space what should I write? Okay, should I write its norm? क्योंकि इसकी जरूरत नहीं पड़ेगी. Okay, norm है वही supremum जो ना हमने, क्योंकि ये exist करता है. So what you do, you define norm of the measure. How do we define the norm of the measure? क्योंकि बाउंडेड वेरिएशन है तो इसमें कैसे करेंगे, तो ऑब्वियसली वही होगा उसका सुप्रीमम, लेकिन सुप्रीमम और हम कहाँ लेंगे, Okay, check here. हम नॉर्म डिफाइन करते हैं उसको, मुझे ये देखना सुप्रीम किस पे लेते हैं। ये हो गया अपना साइन मेजर का नॉर्म। We usually define जो generally होता है ना norm, we usually define it norm of mu to be modulus of mu, which is again a norm that's in general for a measure. So this is the norm for a general measure. So I think it should be the same for norm of finite measure, finitely additive वगैरह वगैरह जो है अपना condition. So इसलिए keep it as it is. I don't think we would need it. So but under this is a normal linear space. ठीक है? So maybe there is some slight change here, but I will check. No issue. So although I don't need it, I think so that's why I haven't written it here. तो theorem हमारा है कि L infinity D का जो dual है, that is all bounded functions on D, it is isometrically isomorphic to BAD and into this space. Here the identification is given by जैसा कि होता है by integral. Actually I think ये दिया होगा एलिप्रेंटिसन बॉर्डर में, ये अच्छे से किया होगा. Mu belonging to BAD if and only if f of f is equal to integral d f d mu, where f belongs to, अब इस आइडेंटिफिकेशन L सब थोड़ा सिमिलर है उससे जो हमने इससे पहले किया था. वहां पे एक फंक्शन यहाँ आ जाती थी है ना, यहाँ पे जो मेजर के साथ ही रिश्ता है, तो प्रूफ इसका सिंपल है, तो दैट्स व्हाई आई हैव नॉट, शायद मैंने इसीलिए नहीं किया था. Now let mu belong to this BAT, then I integrate with respect to this mu, then f of f given by this f d integral over d f d mu satisfy is linear. पहले तो ये linear है obviously है ना, because integral is linear, इसमें तो कुछ है ही नहीं, इसीलिए मैंने कहा ना ये easy है, इसमें हमें check नहीं करना वो integrability whether f belongs जो जैसा LP में था, and mod of f ऐसे लिखते हैं, then f is linear, क्या होगा, and modulus of f would be equal to mod of integral d f d mu. एक्चुअली यहाँ मुझे x लिखा था मैंने, अब ठीक है, ये ऐसे d लिखना चाहिए ना, क्योंकि मैंने एक सेट लिया है उसका नाम d. Okay, f is linear. Now this would be integral less than equal to mod of f d mu. Needless to say what? Needless to say this is less than equal to supremum over x belongs to d mod of fx into integral d d mu, which is equal to norm of f into, of course यहाँ पे mod होगा, sorry, mod of f into mod of f, तो ये है, और ये जो है this is actually mod mu of d, so that is equal to norm of f into norm of mu. So that's the, यहाँ लिखना चाहिए मुझे अंडर दिस नॉर्म, तो अभी मैं शो मतलब यही है. ओके, सो दिस इज इट, व्हिच इंप्लाइज दैट हमें मिला f of f जो कि इजी वाला पोर्शन है हमारा, is less than equal to norm of u, which is a finite number, into norm of f. And of course, it means that f is a bounded linear operator. F is a bounded linear operator for this bounded functions, and capital norm f का जो operator norm है, that will be less than equal to norm of mu. Let's call this one. But to show the conversely, वही हमारा पुराना है लेकिन उससे इजी है जो हमने एलपी में किया था, क्योंकि इसमें वो एग्जिस्टेंस नहीं दिखानी जो दूसरे फंक्शन की है, वो एल क्यू में बिलोंग करेगी, क्योंकि यहाँ पे दूसरी फंक्शन है ही नहीं, मेजर खुद सारा कुछ करता है। तो अगर एफ यहाँ पे है, वी डिफाइन म्यू ऑफ ई, हम एक मेजर डिफाइन करेंगे विद द हेल्प ऑफ दिस फंक्शनल, जैसे कि वहां किया था एफ ऑफ का ई। देन ऑफ कोर्स म्यू ऑफ ई जो होगा, म्यू ऑफ फाई तो ऑब्वियसली होगा एफ ऑफ काई ई, sorry, chi of phi, or this is obviously f of 0 function, that is 0. Then I have mu of, let me write it like this. मुझे क्या चाहिए? मुझे चाहिए it is finitely additive measure. So I have to show that mu belongs to PAT. It has, I want to show that it defines a finitely additive measure in this way. तो मैं लेता हूँ mu, जैसे लेता हूँ for EI, for EI contained in D with EI intersection EJ, ions found N equal to phi for I not equal to J. If I have a disjoint collection of finite sets inside D, then mu of union I runs from 1 to N EI is equal to, by our definition, it should be f of characteristic function of union I runs from 1 to N EI. And needless to say, because these are disjoint sets, this is f of summation I runs from 1 to N xei chi ei. And since it is a linear function, so it would be summation I runs from 1 to N f of chi ei. So what I'm getting, which is by, okay, so we are mu of this thing is equal to this thing, but f of chi ei is exactly summation I runs from 1 to N mu of ei. So that is, mu is finitely additive. Finitely additive. तो अभी मैं दिखाना है, it's a bounded variation also. तो finitely additive आ गया. So let's take a measurable partition of D. So let EI runs from 1 to N be a measurable partition of D, any measurable partition of D. By that I mean D can be written as I runs from 1 to N EI are measurable, and of course they are disjoint pairwise. We know that. So a measurable partition of D है, we get summation I runs from 1 to N mod of mu EI जो है उसको मैं लिख सकता हूँ summation I runs from 1 to N f of chi EI. What I do, थोड़ा सा इसमें हम इंटरचेंज करेंगे, हम लिखेंगे इस तरह से इसको epsilon I into f of chi EI. where epsilon I is either +1 or -1, depending upon whether this is positive or negative. So I can change it like this. F is linear, but I can take the numbers inside, whether it is +1 or -1. I can write f of summation I runs from 1 to n epsilon I chi ei. Now every real number is less than equal to its mod, so it should be less than equal to f of summation I runs from 1 to n chi I xei, which is less than equal to norm of f into norm, जो इसका infinity norm है, because this is a function in L infinity. So this should be summation I runs from 1 to I epsilon I chi ei under its subnorm. So which is nothing but equal to norm of f. Why? Now look at this, what this would be. This would be either +1 or -1. है ना? So we take the supremum of +1s, and because xi's are disjoint, वो भी important है. So this is not, so suppose x belongs to D, so it means x belongs to some particular EI. अगर उस particular EI में वो belong करते हैं, तो इसका मतलब यहाँ पे जो ये sum में numbers हैं, तो वो तो होंगे या 1 या 0, मतलब एक 1 होगा, बाकी सारे 0. अब जो 1 होगा और मल्टीप्लाइड पे होगा +-1, so it would be in any case either +1 or -1, और उसका जो सुप्रीमम होगा वो तो 1 ही होगा. So this is equal to norm of f, which means that is I can write taking supremum, क्योंकि this is independent of EIs, any partition EI, taking supremum over all partitions. That would be exactly our norm, gives okay. So now ये तो हो गया हमारा कि अगर मैं इसको सेकंड मान लूं, by first and second यानी norm तो preserve होता है ना? Now the question is, अभी तक तो हमने ये देखा कि norm of mu is equal to norm of f, लेकिन अभी तक मैंने वो नहीं दिखाया, वो भी rather straightforward है. I have so far defined my I have shown that you can define, look, there is a correspondence between mu and I. If I restrict, I have to show that f of f is equal to integral d ft mu for all f belonging to L infinity t. Now I have shown, by my definition, I have shown that I have defined this to be, by my definition, my measure is defined as, let me write it as f of chi of a, right? So if I take a measurable partition, now since now mu of a is indeed a measure, is a finitely additive measure, is a finitely additive measure of bounded variation on D. I can take a measurable partition, so it would imply that, what would it imply? So mu of D would be equal to f of, should I write it like this or should I write it like an integral? मेरे कहने का मतलब है, it is the same thing as f by a. अगर चूंकि ये measure है, तो it also is the same thing as, should I write, okay, d mu, right? I should write here a, which is the same thing as d over chi a mu. So it means that f of chi a, should I write it? So you have got, for a step function this is true, for a characteristic function, so which means for a step function this is true. So f of f is equal to integral t ft mu for all characteristic functions of measurable sets. Okay, तो so मुझे दिखाना है for all bounded functions ये true है, you know, that's the point. So by linearity मैं ये कर सकता हूँ by linearity of capital F, and of course जो भी इसकी properties है ना, F भी होता है linear, we can show मतलब F of phi is equal to integral t phi t mu for all step functions. So because they are just linear combinations of characteristic functions for all step functions phi, and step functions you know are bounded because their range is actually finite. So they belong there. Finally, now since step functions are dense in bounded functions, the step functions on D are dense in L sub infinity T. Again, that's very easy to actually show. Let's leave it as a home assignment. So by continuity of F, by continuity of this capital F, f of f is equal to integral t f t mu for all f belonging to L infinity t, and we are done. Okay, so that was this. Actually मैं ये theorem तुम्हें कराना चाहता हूँ, ये उतना difficult नहीं था, इसमें उतना काम नहीं था basically. So I wanted to go to Mazur-Ulam theorem. Again, this is for real normal linear spaces. इसको क्या हो गया? तो Mazur-Ulam theorem हमें करना है, which is an important theorem actually, because it says, you know, so far we have assumed, we want to know, जैसे अगर कोई मैप है, अगर वो लीनियर है तो उसकी कंटिन्यूटी मतलब इजी है, मतलब वी गेट सम इजियर कैरेक्टराइजेशंस ऑफ कंटिन्यूटी. जैसे अगर वो एक पॉइंट पे कंटिन्यूअस है तो हर जगह कंटिन्यूअस है ना. लेकिन अब अगर उल्टा हो, मुझे पता हो कि कोई फंक्शन कंटिन्यूअस है, तो अब उसकी लीनियरिटी पे क्या असर पड़ेगा ना, मतलब व्हाट, हमें पता है लीनियर क्या होता है, जैसे हमें पता है कंटिन्यूअस क्या होता है, लेकिन अगर t लीनियर है then it is sufficient that t is continuous at 0. अगर t continuous at, then अगर t is continuous at any point, at some point in particular 0, then t is continuous everywhere, and it is because t is linear. कि एक पॉइंट पे कंटिन्यूअस होना काफी है for continuity on the whole space. Now इसी तरह से रिवर्स में अगर हम सोचें, suppose I know something about the metric, of course t is linear. No, मैं कह रहा हूँ suppose I don't know t is linear, तो मैं वही कह रहा हूँ suppose t is continuous, उल्टा, तो क्या मैं कंडीशन लगा सकता हूँ plus something so that it becomes linear. जैसे यहाँ पे था ना, लीनियर को अगर हम एक पॉइंट पे कंटिन्यूअस लें, या फिर ये बता दें कि अगर डोमेन बाउंडेड है तो रेंज भी बाउंडेड है, या t of x is less than equal to k times norm of x, it is equivalent to saying that t is continuous everywhere. So in the reverse direction, I've got Mazur-Ulam theorem for real normal linear spaces. So let me, should I state it कि पहले हमें थोड़ा इसके लिए कुछ तैयारी करनी पड़ेगी. Okay, let's first write down the theorem. Let x and y be real normal linear spaces. Real normal linear spaces, and t from x to y be a surjective isometry. Surjective आइसोमेट्री नोट ये मेट्रिक को प्रिजर्व करता है, और चूंकि नॉर्मल लीनियर स्पेस है तो इसमें जो मेट्रिक है इट इज गिवन बाय द नॉर्म इन दिस वे, दैट इज आई मीन दैट द डिस्टेंस बिटवीन tx and ty is equal to norm of x minus 1 for all x y belonging to x, राइट। लेकिन देखो अगर मतलब यहाँ थोड़ा कंफ्यूजन हो जाता है स्टूडेंट्स को, क्योंकि हम लीनियर होता है ना हमारे सारे मैप्स, हमारा ये बाय assumption लीनियर नहीं है, यानी दिस इज नॉट t of x minus y, क्योंकि अगर हम पिछले थियरम्स में हम ऐसे ही करते थे ना, क्योंकि वहां पे assumption है, तभी हम बाउंडेड लीनियर ऑपरेटर्स पे ही सारा करते हैं ना। तो यहाँ पे हम ये नहीं मान रहे, हम मान रहे हैं ये सर्जेक्टिव है और ये मेट्रिक को प्रिजर्व करती है। एंड देन t इज लीनियर, अगर ये सच है then t is linear provided, हम इसमें भी और एक्स्ट्रा कंडीशन लगा रहे हैं, t of 0 is 0, it sends 0 to 0. So that's our Mazur-Ulam theorem. लेकिन इसको करने के लिए हमें थोड़ा प्रिपरेशन करनी पड़ेगी, क्योंकि हम इसमें यूज काफी सारी चीजें करते हैं, एक दो डेफिनेशंस और एक दो रिजल्ट्स। उनमें पहला वाला है, okay, now let's define what's an affine map. Now T is affine map. Should I say a map T from x to y, where x and y are vector space, यानी इसमें norm का कोई connection नहीं है, are linear spaces over some field K over R देते हैं, या over K भी चल सकता है, लेकिन ये रिजल्ट हम कर रहे हैं for real normal linear spaces, so that has to be taken care of, is said to be affine if it basically preserves convexity. If for all alpha belonging to 0, 1, t of alpha x plus 1 minus alpha at y is equal to alpha times t of x plus 1 minus alpha times t of y. So that is the definition of affine map. You could have actually, जैसे हम लेंगे real numbers में y is equal to x plus 3. Now this is an affine map, it's not linear. बजाय इसके अगर मैं लिखूं t of x अगर है x plus 3, this is not a linear map. Why? Because t of x plus y जो होगा वो होगा x plus y plus 3, और t of x जो है t of y जो होगा वो होगा y plus 3. Obviously x plus 3 plus y plus 3 is not equal to x plus y plus 3. So it's not a linear map, but this is an affine map, because if I take t of alpha x plus 1 minus alpha times y, this would be alpha x plus 1 minus alpha times y plus 3. Even a 3 ऐसे लिया, it would be any constant actually. Then, but I can write it as alpha into, should I write it alpha into x plus 3 plus 1 minus alpha into y plus 3. तुम इसको ऐसे लिख सकते हो, because यहाँ पे मैंने plus alpha 3 और minus alpha 3 लिखा है. Now I can write here plus alpha 3 minus alpha times 3. तो वो 0 है, तो minus alpha 3 यहाँ आ गया, और 3 तो है ही, और plus alpha 3 यहाँ आ गया, which is the same as alpha t of x plus 1 minus alpha times t of y. So there are maps which are affine, but they are not linear. That was just a simple example. Now, basically, affine is, for a real space, affine is almost a linear map. By almost, I mean this theorem, जो हम करेंगे, it is just चलो मुझे लगता है मैं इसको स्टॉप करता हूँ, लेस देन 1 मिनट है, तो क्योंकि ये फिर से तुम जॉइन करो जल्दी।